In this video, we're going to be introduced a few words that pertain to chemical equilibrium. We'll also be able to identify on a graph when chemical equilibrium is reached. We have an example of a chemical reaction going to equilibrium here. Inside the bottle, there is a special sugar. There's also sodium hydroxide and a chemical dye called methylene blue. Methylene blue is a chemical that is colorless or blue. Right now he just mixed the chemicals and he's waiting for it to go to equilibrium. Now it's at equilibrium. Note that it's clear, but he's going to mess up the equilibrium. Oh my god! I'll stop talking. So the reason why it turns blue is because the reaction can go in reverse. Shaking the bottle makes it go in reverse because it introduces oxygen in the solution, which reacts with the methylene blue. But the important thing to note is that it will go back to its equilibrium state. So the key idea to understand right now is that some chemical reactions are reversible. Also, some chemical reactions can reach an equilibrium state. Well, what's an equilibrium state, you might ask? It's a state in which both the reactants and the products are present in concentrations that are no longer changing. So in the flask on the left, there's actually still some reactants stored inside the mixture. Equilibrium reactions don't go to completion. That is, not all of the reactants will be turned into products. There's still reactants left. I want to show you a very important reaction called the Haber process. That's an equilibrium reaction. This reaction is really important because this is how we get NH3 or ammonia for agricultural fertilizer, for our food. Food! So in this chemical equation, you should notice that there's a double arrow. This represents an equilibrium reaction. The forward reaction refers to creating more products in the equilibrium reaction. You can see the nitrogen gas reacting with the hydrogen gas in the forward reaction to form products. Watch closely on the image. Ooh, did you see it? The reverse reaction refers to creating more reactants in an equilibrium reaction. And now we can see the ammonia decomposing back to the reactants. Watch closely. Nice. Here we have a graphical representation of reaching a chemical equilibrium for the Haber process, the equilibrium reaction we just saw. This graph shows what's happening to the amounts of reactants and the amounts of products over time as equilibrium is being established. Take a moment to see if you understand what's basically going on in this graph. Pause the video if you need to. You should notice that at the beginning of the reaction, there is only reactants and zero product. As the reactants are decreasing, product is being produced. That makes sense. Eventually, the amount of reactants and products both plateau, which means that their amount is not changing anymore. The reaction has reached equilibrium at this point. It's important to note here that the amount of reactants and products is not the same. This is a big misconception that most students have because it sounds like equilibrium means that everything is equal. But this is not entirely true. Here you can see that there is more hydrogen gas at the end, followed by ammonia, and that at the end there is not much nitrogen gas left, according to the graph. Here are some key ideas that you should know for chemical equilibriums. During a chemical equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. This leads to the second point. If the rates are the same, then that means the amount of the reactants and the amount of the products does not change. However, the amount of the reactants does not equal the amount of the products though. I'm just going to plug in one last definition here. Dynamic equilibrium. Dynamic in the phrase dynamic equilibrium means that even though the equilibrium is reached, the forward and the reverse reactions are actually still happening. It looks like the reaction has stopped, but it only looks that way because the forward rate of the reaction is equal to the reverse rate of the reaction. So there is no net change happening. I want you to try a little bit of practice with the vocabulary now. So on a piece of scratch paper, or I guess in your head, you can write a few sentences about a chemical equilibrium to the best of your knowledge that includes those words below. Underline those words. So I'll give you some time, pause the video, and then you can resume the video to see an example. All right, so instead of me showing you what I would write, I would actually show you what one of my previous students has written in this nice index card. All right. Chemical equilibrium is when the rate of products and reactants being exchanged is equal. Chemical equations have a forward equation, which the reactants are creating products, and a reverse equation, which is how the products create more reactants. True. To show both of them at the same time, the original forward equation is shown but with a double arrow, signifying both equations at once. Once the products and the reactants cease to increase or decrease, or remains a stable number, equilibrium has been reached. Yes, that's true. While the rate of the products and reactants being created is the same, the amount of each does not have to be equal. Yes, that is very important. That last bit is the biggest misconception that students have, but this student understands that during equilibrium, the amount of reactants and the amount of products does not have to equal. It could be different. They're just not changing. All right, so I'd give the student an A+.